Hi, I'm Miss Hearn. Let's get started.
Okay, so you might be wondering, well, if inverses are supposed to have opposite operations, and these two have opposite operations, one is doubling, one's taking half, one is adding 3, one's subtracting 3, why did these not work out? So to get an idea for that, we're going to actually find the inverse of 2x plus 3. There is a procedure we can use to do that. To find the inverse of a function, we're going to use the idea back here. You remember how the two functions had the same point but with just the coordinates reversed? Well, that's true in general. So what we're going to do is we're going to switch all the x and y coordinates to find the inverse of a function. The steps that you're going to use are these. You're going to step 1, replace f of x with y. It's kind of messy, so I'm going to write it again. Replace f of x with y. This is just because it's easier notation to work with a y rather than an f of x. And then we're going to switch all the x's and y's, literally switch the variables around. Anywhere we see an x, we're going to put a y, and anywhere we see a y, we're going to put an x. And then we're going to solve for y, and then we will have our inverse function, but we got to give it its name. So in the end, we're going to replace the y with the notation f inverse of x, function notation for an inverse. Okay, so those are the steps that we're going to use. And the function we're going to try it out on first is the one we were just looking at, which is f of x equals 2x plus 3. Okay, so step 1, instead of writing f of x, we're going to write y equals 2x plus 3. That's step 1. Step 2, we're going to switch the x and the y coordinates. So where we have a y, we're going to put an x. Where we have an x, we're going to put a y. But everything else is going to stay in the same position. Step 3, you're actually going to solve for y in this equation. Okay, so solving for y. What should I do first to solve for y here? I want to get y by itself. What should I do? I agree. We should subtract 3 from both sides. So that's going to give us, I'm going to turn the equation around though. This is going to mean that 2y is equal to x minus 3. And then what should I do? Very good. We're going to divide by 2 now. So that means that we're going to have y equals x minus 3 over 2. Okay, so you could go further and you could write it as, say, y equals 1/2 x minus 3/2. But I want to focus for a minute on this version of what we just found. Remember I said that we're supposed to reverse the operations. And so in fact, this does reverse the operations. In the original function, we're adding 3, and here we're subtracting 3. And in the original function, we were multiplying by 2, and here we're dividing by 2. How is this different than the g of x up here that didn't work? Well, not only are we reversing the operations individually, but also the order in which we do them. We have to backtrack. So in the original function, we first took any number that was plugged in, we first doubled it, and then we added 3 to that. So to reverse that, you have to work backwards. So you'll see here, first we take the number and we subtract off that extra 3, and then we reverse the multiplication by dividing. In fact, our correct inverse function, which we're going to give the name f inverse of x, is 1/2 x minus 3/2. You, again, can write it in either format, but usually we write lines in this format here. Okay, so step 4, replace y with the symbol f inverse of x, and you have your inverse function. And I don't need to confirm this, but if I did take the composition of these, you would get an x. We know that because we followed this 4-step process. Okay, so we've learned a couple of important things about inverses. Another important thing has to do with their graphs. So here are the graphs of the two functions we were just working with. F of x equals x plus 3, and f inverse of x equals 1/2 x minus 3/2, the inverse that we just found. By plotting their y-intercept and using their slopes, you can easily come up with this graph. And I just want to point out that the graph in red, the original function, and the graph in blue have a certain relationship. For example, all of the x's and y's are switched, right? So one function goes through 1, 4, the other one goes through 4, 1. One function goes through 0, 3, the other one goes through 3, 0. One function goes through negative 3 halves, comma 0, the other one goes through 0, comma negative 3 halves. And because of that, they end up being what's known as symmetric across the line y equals x. In gray here, I've penciled in y equals x. And you can see that each of these is exactly the same distance on the opposite side of that line. It's a reflection. If you were to draw this on a sheet of paper and fold across the line y equals x, these two graphs would match up. Okay, so that's another characteristic of inverse functions. You can tell they're inverses by looking at their graphs, because one is a reflection of the other since we've switched all the x and y coordinates.
I hope you found this video helpful. If you did, please give it a thumbs up. That helps other students to find the video. In part 3, we'll discuss a summary of all the big ideas about inverses.